All right, this is exam 5 for physics 202. First, just wanted to select the correct ray diagram. So first, let's see, this is what the object looks like. So here, the ray comes off parallel to the axis, and then it goes, well, the ray wouldn't actually go like that. It would go like that because this is a diverging mirror, so that's not correct. And then on this one, parallel to the axis, diverges such that if it were to trace it back, it would go through the focal point. Here it goes through the focal point. Or excuse me, no, that's not right. It should go through this focal point over here. In fact, this isn't really a focal point at all. And then it would go parallel to the axis. So that second one's not right. Here we come up. It's as if it's coming out of the focal point, but then it should go in this direction. So that one's not right. So this one has to be the right one. Let's see, parallel to the axis through the focal point. That is, it comes up like this, such that if you trace it back, it goes through the focal point. Here it goes forward as if it's going from the focal point, and then it goes parallel to the axis. So D is the right answer. Here I have a convex lens. Here it is through the focal point, parallel to the axis through the focal point. And then this should actually go straight, so that one's not the right answer. Here we go up through the focal point, parallel to the axis through the focal point, and then through the center of the lens. And then you trace them all back so that they cross, and so that is the correct one. A negative magnification indicates that the image is inverted. Actually, let's go back and look at those other two. So here, this one is just all wacky. It's not coming from the focal point. It's not parallel to the axis or any of that. Here we have one that comes up to the focal point and then parallel to the axis. And that would be okay. And then this one goes parallel to the axis, and it should go through the focal point. So the second one's not right. Convex lens produces an image twice the size of the object. The object must be placed inside the focal point. All right, so that would be half a focal length in front of the lens. Which of the following can make a real inverted image? That would only be a convex lens. Remember, a convex mirror, that's like a security mirror. A concave lens is like that. A convex lens is like this, and it can make a real inverted image. A spherical mirror can have which of these aberrations? Not chromatic, because there's no refraction, just B. The easiest way to correct for spherical aberrations is to use an aperture. The human eye has a lens that can change its focal length. What is the focal length of the eye's lens the largest? Okay, this is the eye. When you have something that's really far away, light rays come in, they focus at the focal point, and then the focal point is at the retina. So it's when the object is very far away that the focal length is equal to the diameter of the eyeball. Concave lenses and convex mirrors look like this. Convex mirror looks like this, are diverging. What type of lens is this? Well, it's convex on this side and planar on this side, so plano-convex. Mirages are a result of refraction. Because of atmospheric refraction, the sun appears at sunset even though it is below the horizon. For a single lens system, virtual images are always on the same side as the object. So this is like a magnifying glass. Like this is my object, this is my image. Always on the same side. This is a virtual image. I stand 1 meter in front of a flat mirror. What is the distance between me and my image? So here I am. This is 1 meter. My image is likewise 1 meter. So the distance from here to here is 2 meters. A flat mirror may form a virtual image only behind the mirror. All right, let's look at this scenario. This is 32 centimeters. I'll call this P1. All right, first I want to find Q1. All right, so that's Q1, and then M1. right? And then that means that the image is going to be 8 centimeters. It's going to be 1/3 the size of the object, and it will be inverted. All right, so if this distance is 8, that means that this distance is 24. 24 plus 8 is equal to 32. So P2 is equal to 24 centimeters. Then I can solve for Q2. 1 over F2 minus 1 over P2. What was P2? Oh, 24. 3 over 24 minus 1 over 24. And then I can find my magnification. All right, so the final magnification is the product of these two, which is positive 1/6. What I was asking for, the magnification? Yes, so positive 1/6, and it's 12 centimeters to the right of the second lens. All right, draw 3 rays for this object. All right, parallel to the axis, through the focal point, that is as if it's originating from that focal point, and then parallel to the axis, and then through the center of the lens. All right, and I can trace these back. So my image is going to be right here. It is a virtual image. It is upright, and it is bigger. This is like a magnifying glass. Mirror produces an upright image of an object. All right, so it's upright. That means that the magnification is positive. The height of the object is 4 centimeters. The height of the image is 2 centimeters. Tells me that the magnification is plus HI over HO, plus 1/2. Mirror has a focal length of 20 centimeters. All right, I want to ask myself, is this going to be positive or negative, or what type of mirror is this? This has to be a convex mirror because it's that is like a security mirror because it's an upright image. It is an upright image that, let me fix this. An upright image that is smaller. That is a convex mirror. It is also a virtual image. So that tells me that my focal length is a negative 20 because convex mirrors have a negative focal length. Okay, and I want to know where is the object located. So where is P? I also don't know Q. All right, so I have two unknowns here. I have two equations. M is equal to negative Q over P. I have 1 over Q plus 1 over P equals 1 over F. I want to know P, so I can solve this one for Q. I get negative PM. And since I'm looking for P, I can come over here. I have a 1 over negative PM plus 1 over P equals 1 over F. And I know everything here but P. Let's see, I'll put in some numbers here. Magnification, so this is negative 2 over P plus 1 over P equals 1 over negative 20. Negative 1 over P equals negative 1 over 20. So P is equal to 20 centimeters, and that's the right answer. Optometrists use the power of a lens, which is the inverse of the focal length, where the focal length is in meters and the power is in diopters. Let's see, magnification is equal to negative 1. P is equal to 5 centimeters. I need to find the focal length. So this is a similar problem to what I had before. And then once I find the focal length, I'll find the power. I know that the magnification is negative q over p. 1 over f equals 1 over p plus 1 over q. It's from the lens equation. I want to solve this equation now for f. So this is equal to negative 1. So those negatives cancel. So I'm just left with p is equal to q. And I'm looking for q, so I can plug that in over here. 1 over f equals 1 over p plus 1 over p. And now I can plug in my value for p. So 1 over f equals 2 over 5. So f is equal to 5 halves, or 2.5 centimeters. And now the second part of this is to find the power. That's going to be 1 over 0.025 meters, which gives me 40 diopters. And Ansel places an object 30 centimeters from a thin convex lens. The real image forms at a distance of 10 centimeters from the lens. So Q is equal to positive 10 centimeters because it's a real image. What is the focal length of the lens? This one's pretty straightforward. F equals 1 over P plus 1 over Q. That seems too simple, is it? No, that's it. All right, so this is 1 over 30 plus 2 over 30 plus 3 over 30. That's 4 over 30. 30 over 4. Let's see, 4 goes into 30, 7.5 times. And so that's the right answer, and that's the final answer. There's the multiple choice answers.